So if we start with a Lagrangian that's a function of a bunch of variables q1 up to qn and their derivatives and time, then for each variable qj we have an Euler-Lagrange equation that looks just like this. Now in certain cases, the Lagrangian doesn't depend on one of the variables at all. The classic example would be a free particle where the Lagrangian was just the kinetic energy term. And yes, it depends on x dot, y dot, and z dot, but it doesn't depend on x or y or z explicitly. So in that case, this term here would be 0. In that case, this thing in here is clearly conserved. And by conserved, I mean that its time derivative is 0, so whatever value it has initially, it has for all time. And this quantity here is sufficiently important that it is called the generalized momentum, or sometimes the canonical momentum. So we can see from here that if we take this derivative, then in this example, p of x would be dl dx dot, which is just mx dot, mass times velocity. So it's the normal momentum for the normal free space thing. If this were an angular coordinate, if we had an angular coordinate, we would find that it's actually the angular momentum. And indeed, whatever coordinates we have, we just take the derivative of the Lagrangian with respect to that time derivative of that coordinate, and that gives us the generalized concept of momentum. And what we know, of course, is that when the Lagrangian does not depend on a variable, then we have a conserved quantity, which is this generalized momentum.